So cryptography, we are going to discuss. This is the concepts and the techniques, which is the fifth part of the unit number 1. Uh, First of all, we are going to discuss about the encryption and the decryption, because we know that we are in requirement of securing the information which is flowing from one person to another person, and for that particular purpose we will be using certain algorithm as well as the process by which we are going to hide the message into a non-readable form, because whenever we will be sending the messages in the readable form, anyone sitting in between the sender and the receiver can have that information, because it is readable, it is understandable. So whatever conversation which is going on in between sender and the receiver, it is being taken care by another person who is sitting in between. So the process by which we can do is the encryption process, in which we are converting the plain text into a ciphertext. Now, what is the meaning of plain text and the ciphertext? Plain text means something which is readable, understandable, and the ciphertext is a kind of a text which is converted from the plain text to another text which is non-readable. By reading the ciphertext, you are not able to find out that what is the meaning of the information or the message which has been sent. So plain text is a readable form, as ciphertext is a non-readable, non-understandable. So the process by which we are converting the plain text into the ciphertext, that process is called encryption process. As well as, so whatever sender will be doing, whatever plain text or the messages in the readable form is available with the sender, what he used to do, he used the encryption algorithm. He used to do the process of encryption and converting that plain text into a ciphertext. So this ciphertext is being sent by the sender to the receiving end, and whenever receiver used to receive, it is not receiving the information in the form of a plain text, but it is receiving the information in the form of a ciphertext. So whenever the plain text is converted into a ciphertext, there must be another process by which the ciphertext can be back converted into the plain text, so that the receiver will be able to understand that what kind of message has been sent. So encryption is a process which is being done at the sender side, and the decryption is a process which is being done at the receiver side. Of course, the ciphertext will be traveling in between the sender and the receiver in the network, so that anybody else who is sitting in between will be not able to get that what kind of information has been sent by the sender to the receiving end, because he is not able to understand, one is not able to understand the ciphertext since it is in the coded form. So the process is called encryption of converting plain text into a ciphertext, and the process of converting the ciphertext back to the plain text is known as decryption. So of course we will be using some kind of algorithm. So the encryption process, as I told you, it is being done at the sender side, and the ciphertext will be traveling on the network, open network, and whenever it is being received by the receiver, it converts the ciphertext back to the plain text by using the decryption process. So we have encryption algorithm by which we are doing the encryption. We have decryption algorithm by which we are doing the decryption. So that algorithm is known as encryption algorithm as well as decryption algorithm. Now, encryption algorithm and decryption algorithm both are counterpart of each other. How it is counterpart of each other? Meaning thereby the process by which encryption is done, same process will be adopted to decrypt it. So as far as the encryption and the decryption, of course, it is related to the algorithm. So, and this algorithm is known to each and every person, because we know the process how to do it, how to convert the plain text into a ciphertext, and how to convert the ciphertext back to the plain text. It is known to each and everyone. So as far as the encryption and decryption is concerned, there are two important aspects which are related to these processes. The first one is the algorithm, and second one is the key. So then, what is the meaning of the key? Because this is the second issue which are related with the encryption and decryption. But this key is the most important part, which is related to the cryptography. Now, you can consider this key is very much similar. Now, you can take an analogy that whenever you want to secure anything, you will be using the lock and the key. Whenever you want to secure, you put a lock using the key, and when it is locked, whenever you want to open it with the help of key, you are going to open it. So you can consider this encryption and decryption process, which is having two aspects. Algorithm is similar to the lock, and key is similar to the key, which is used to close the lock or the open the lock. So algorithm is a lock, and the key is the key. So every time whenever we are discussing lock key pair, meaning thereby algorithm key pair. So in general, the algorithm which is used for encryption and decryption, it possesses usually it is known to everyone, but it is the key which is very important. If you talk about if you go to the analogy of lock key pair, and if you talk about the digital lock, so you might have seen that there is a certain code by which it is being logged, and with the same code it is being opened. Now that code is actually the key. Similarly, whenever we are doing encryption and decryption process, we are adopting an algorithm by which we can convert plain text into ciphertext or ciphertext into plain text. But the most important part is, besides knowing the algorithm, we must have a key by which it will be logged, by which the algorithm will be imposed on the messages, so that encryption and decryption can take place easily. So key is also an important issue, and we will discuss more about that key later on whenever time comes. Now, as far as the cryptographic techniques are concerned, we have two kinds of cryptography technique which are often used. The first one is the symmetric key cryptography, and the second one is the asymmetric key cryptography. Now, the difference between these two cryptographic techniques, of course, both cryptographic techniques are used for conversion of the process that is called plain text to the ciphertext and the ciphertext to the plain text. But the difference in between these two techniques are that in case of symmetric key cryptography, we will be using same key for encryption process as well as for the decryption process. That key is called shared secret key, or you can call it as a common key. So in case of symmetric key cryptography, we will be using only single key whenever we have to lock the process or unlock the process, whenever we have to convert the plain text into a ciphertext, or we have to convert ciphertext back to the plain text. But in case of asymmetric key, we use two different keys for encryption and decryption. One key is used for encryption and another key is used for the decryption, meaning thereby the key which will be used for encryption, conversion of plain text into ciphertext, the same key will not be used for decryption process, that is from ciphertext back to the plain text. So in that case, in asymmetric key cryptography, we will be using different key for converting the ciphertext back to the plain text. So the keys which are used, so it means in symmetric key cryptography, one key is used, but in asymmetric cryptography, two keys are used. So in symmetric key cryptography, whatever key is being used, that is called shared secret key. But in case of asymmetric key cryptography, in which we are using two keys, the first key is known as public key and another key is known as private key. This is not a right time to discuss more about the asymmetric cryptography, because we are starting with the symmetric cryptography. And in that symmetric cryptography, we will discuss first, and then later on, whenever time comes, we will discuss about the asymmetric key. But right now, we are able to understand the difference between these two cryptographic techniques. Now, As far as the symmetric key cryptography, which is the main focus of this particular lecture, in case of symmetric key cryptography, as I told you, the shared secret key is being used. When we are using shared secret key, it means there is only one key which will be used for encryption as well as for decryption. So whenever we are using the same key for the encryption, the decryption, the sender as well as the receiver must know both the keys, and that is the important issue which is related to the shared symmetric key cryptography. It is also called shared key cryptography. So they must have an agreement. The sender and the receiver must have an agreement so that they will come upon in a conclusion that they will be using a particular key for the any kind of conversation. Now, uh, there are certain problems just because of the only one shared symmetric key is being used in symmetric key cryptography. There is two important issues which are related with this symmetric key cryptography. The first and the main issue which is related to the symmetric key cryptography is the shared secret key. How to exchange the key so that the sender and the receiver will be receiving, will be having the same key at the same time so that the conversation can take place in between the sender and the receiver. Because if sender is sending any message for a legitimate receiver, then and the sender doesn't want that anybody else who is sitting in between uh, in the network will not be able to know what kind of message has been sent. So it means whatever key he will be using to lock the message, to encrypt the message, must not be known to anybody else besides the receiver. So there must be an agreement with which the sender and the receiver will start the conversation. But before they start the conversation, as I told you, they must come into an agreement that what key will be used, and both the sender and the receiver, must know that what key will be used for the encryption and the decryption. Because again, I am repeating, the same key will be used for converting plain text into ciphertext, and the same key will be used for converting the ciphertext into plain text. That is called encryption and the decryption process. So the first problem which is related with the symmetric key cryptography is the exchange of the key, because it is not necessary that the two persons who want to be in conversation may not be very near to each other. It may be possible one is sitting in some place and another is sitting thousands of miles away. So they must have an agreement. And how they can make an agreement? So the first agreement with which it can be done, that whatever sender has assumed a particular key, it sends that key by post to the receiver. But this is not a solvable problem, because anybody who is in between, when the envelope will be in transaction, anybody can know what will be the key. So the first point is going to abolish. So second point is the key should be sent through the hand delivery or the courier, by which the sender and the receiver will be able to know that what key will be used. But this is also not safe. Then the third point, with people come with the idea, why not to put that key into an envelope, put that envelope into a box, seal the box by a secure lock, and then send this box to the receiver. Of course, this is a safer side. But how, whenever the receiver will be receiving the box, how it will be able to open that box, because the key is not available to them. So the people come with the idea, why not to send key separately from the sender side to the receiver through the network. So once you are sending the key on the open network, again the people who are sitting in between can able to find it, that what the key which is going to be used in between these two persons. So the people come with the another idea. Then the idea is that why not the sender and the receiver are meeting at a certain place at a certain juncture and hand over the key and make an agreement that this key will be used. But this is not possible at all, because It may be possible. It may be situation that A is sender and B is the receiver, and A will be in Gorakhpur and then B will be in Lucknow or Delhi or Bangalore. So it is not possible to meet personally and hand over the key. So the first problem which is related with the symmetric key cryptography is the key distribution or the key exchange. Now, this is not only the issue, there is a second issue which is related with symmetric key cryptography. The second issue which is related to the symmetric key cryptography is the number of keys to be used in between the two different users. Now, I am giving you an example. Suppose there are two persons in the network and they want to have a secure conversation in between. Suppose these two persons are A and B. So these two persons will be requiring one key lock pair. But suppose there are three persons who want to communicate A, B, and C. Then in that particular case, how many keys will be required for the secure conversation? One key will be required to make a conversation in between A and B. Another key will be required to make a conversation in between A and C. And another key will be required so that B can make a conversation with the C. So it means if there are two users, we are using only one key, but if there are three users, we are using three. And why it is so? Because if A and B are sharing the symmetric key or the shared secret key, and the same key is known to C, then if C is also knowing the key which is being shared in between A and B, then the message will not be safe. It will not be secure, because C will be able to find out that what kind of conversation is going on in between A and B. So that is why there must be a separate key by which A and C can communicate. There must be a separate key so that B and C can communicate. Now, instead of three users, if there are four users, A, B, C, D, then how many key will be required? The key will be required will be A, B, A, C, A, D, B, C, B, D, and C, D. It means there are 6 keys will be required. If there are 5 users, A, B, C, D, E, then we will be requiring 10 key. Whenever we talk about key, I am talking about key lock pair. So, meaning thereby, if A is a person and he has to communicate with 100 persons, and for each person he has to use a separate shared symmetric key. So, how many keys he has to handle? Because if A is making a conversation with B, if A want to make a conversation with C, A want to make a conversation with D. For every person, if A wants to make a conversation, there must be a separate key. So, if two persons are there, we are requiring one key. If 3 persons are there, we are requiring 3 key. If 4 persons are there, we are requiring 6 key. And if there are 5 persons, we are requiring 10 keys. Similarly, the number of keys are going to be more and more and more. So total number of lock and the key pairs in case of symmetric key cryptography is n into n minus 1, where n is the number of persons available in the network. So if there are 1000 users, then number of keys to be handled will be 1000 into 1000 minus 1 by 2. That is 499,500 lock key pair. It's a huge amount. And which key will be used for which pair? It is very difficult to find out. Now, if you want, you can put, if there are 3 persons in conversation, and you can find out that whether this formula, whatever is written, that n into n minus 1 is correct or not. If there are 3 persons, so 3 into 2 divided by 2. 2 will cancel out and it will be equal to 3. If there are 5 persons, I have told you that 10 keys will be required. So n will be 5. 5 into 4 divided by 2. 5 into 4, 20. 20 divided by 2, 10. So the second problem with the symmetric key cryptography is the large number of keys to be handled. But besides having these two problems, one is key exchange problem, second one is the large number of keys, even though symmetric key cryptography is said to be the most used cryptographic technique. Now, the first problem, which is related with the key exchange problem, the people come with the idea and the algorithm which is given by Diffie-Hellman, uh, and that algorithm is known as Diffie-Hellman Key Exchange algorithm, which seems to be very secure, that two persons who want to make the conversation securely with the help of symmetric key cryptographic technique, they will be using Diffie-Hellman Key Exchange algorithm to share the secret key by following the steps which are given by the Diffie-Hellman Key Exchange algorithm. It is going to solve the problem of key exchange. And if there are two persons, Alice and the Bob, who are deciding that they want to make a conversation, so they will be securely able to make a key exchange and come to an agreement that this will be key. In this particular case, in case of key exchange, Diffie-Hellman, no secrets are exchanged, yet they are going to agree upon a particular secret key and how it works. Let us go with that. This is the algorithm with which the two persons has to follow to have a secured key exchange. So first of all, if there are two persons, the Alice and the Bob, they agree on the two large prime numbers, and these two large prime numbers are n and g, and these two integers need not to be kept secret, and Alice and Bob can use to an insecure channel to agree on them, meaning thereby any one of these two will be able to generate a large prime number that is known as n and g, that is designated as n and g, and it is need not required to be made secret, and it flows in the open channel, insecure channel, so that anybody else who is sitting can find out that what is the value of n and g, because it is not going to harm any. It is not going to harm the conversation in between Alice and the Bob. Now, after exchanging the value of n and g, which is a large prime numbers, the first person, Alice, chooses another random number x, and this random number x, which has been chosen by Alice, should not be known to anybody else. It has to be kept secret. Alice will keep this x value secret with himself and calculates the value of a, and this value of a is equal to g to the power x mod n. Now, how it will calculate the value of a? Now, if you go, they have already agreed upon g and n, which are large prime numbers, and the x number is a number which is being supposed or assumed by the Alice. It is known to him, and so a is able to calculate the value, that is g to the power x mod n. Now, what Alice do? It sends that number a, whatever it has calculated, to the Bob, in the receiving. Bob independently chooses another random integer y and calculates b is equal to g to the power y mod n. Now, Bob also know the value of g n, and since it has assumed the value of y, so it also know the y. So by knowing the value g, y, and n, it is able to calculate the value of b. And then, after calculating the value of b, Bob sends this value b to the Alice. So what has been done till now? They have agreed on g and n. Alice has calculated a, Bob has calculated b. Alice, when it has calculated a, it will send it to Bob, and Bob, when it has calculated the value of b, it will send it to a. And now the secret key will be computed. The secret key will be computed by Alice. How it will be calculating? It will be calculating k1 is equal to b to the power x mod n. X is known to him. B, which he has received from Bob, n is already known. And similarly, Bob now computes the secret key k2. Kaise? And how it will be done? K2 will be equal to b to the power y mod n. Actually, it is not b to the power, it is a to the power y, because it has received a. It is wrongly written here. It is a to the power y mod n. So K1 is being calculated by Alice, K2 is being calculated by Bob, and whenever K1 is calculated and K2 is calculated, both are same. Whenever we calculate K1, it will be same as calculated by K2. And how it is possible? How it is possible? Just I am going to give you a very small idea about that. Now, Alice has calculated K1 as b to the power x mod n. B is already calculated as g to the power y mod n. So when we put the value of b over here as g to the power y mod n, the value of K1 will become g to the power xy mod n. Similarly, K2 is calculated as a to the power y mod n, and a is already calculated as g to the power x mod n. So whenever put the value of a is equal to g to the power x mod n, it will be calculating at g to the power xy mod n. So anyhow, we are calculating K1 at the Alice side, we are calculating K2 at the Bob side, and both values are actually equal to g to the power xy mod n, g to the power xy mod n. And whenever we calculate g to the power xy mod n, both the value K1 and K2 comes similar. This is the illustration how this Diffie-Hellman key exchange algorithm used to work. Alice and Bob agrees on the two large prime number, that is n and g, and they have already have a conversation with which they are knowing the value of n and g. And then Alice is calculating a to the power gx mod n, and then sending this value a to the Bob. Bob is calculating b is equal to g to the power y mod n, and after calculating b, it will be sending it to the Alice. Alice will be calculating k1 is equal to b to the power x mod n, and K2, Bob is calculating K2 as a to the power y mod n, and you know b is equal to g to the power y mod n. If we put here, we will be getting g to the power yx mod n, and whenever we are calculating K2 at the Bob side, it will be g to the power xy mod n. So that is why it turns out that K1 is equal to K2 is equal to K. So K thus becomes the shared symmetric key in between the Alice and the Bob. This is how the Diffie-Hellman key exchange algorithm used to work. Now this is an example of a Diffie-Hellman key exchange algorithm. Of course, it has been suggested in the algorithm that n and g should be a large prime number, but calculation point of view, I have taken an example in which very small prime number has been taken as the value of n and g. N is equal to 11 and g is equal to 7. So when n is equal to 11 and g is equal to 7, it is known to Alice as well as the Bob. Now Alice has chosen x is equal to 3. So what it will be calculating? It will be calculating the value of a, that is g to the power x mod n, that is 7 to the power 3 mod 11. This comes 343 mod 11, that comes around 2. Now Alice sends this value of a, that is 2, to the Bob. Similarly, Bob independently choose y. Suppose the y is equal to 6, and it calculates the value of b is equal to g to the power y mod n, that is 7 to the power 6 mod 11, and it comes around 4, and this value b is equal to 4 is sent to the Alice by the Bob. Now K1 is being calculated by the Alice and K2 is being calculated by the Bob. How K1 is calculated? B to the power x mod n, that is 4 to the power 3 mod 11, that comes around 9, and b now Bob now computes the secret value K2 as K2 is equal to a to the power y mod n, that is 2 to the power 6 mod 11, that also comes 9. So that is how this K1 and K2 is coming equal as 9. So on the same network, with assuming certain large prime numbers as well as secret assumption of the value of x at the Alice side and the value of y at the Bob side, they are by applying Diffie-Hellman key exchange algorithm, they are able to come into an agreement of the shared secret key. In this example, that is equal to 9. Now this 9 will be used later on as a key value to encrypt the message by using a certain algorithm which comes under the category of symmetric key cryptographic algorithm to encrypt the message, And when this encrypted message is being received by the receiver will be using 9 as a key, using the same algorithm which is used for the encryption to decrypt the ciphertext back to the plain text. That is why 9 is, which is the key, is more important than the algorithm, the process by which encryption encryption and decryption can take place. So Diffie-Hellman key exchange algorithm is well enough for applying the symmetric key cryptography with the help of shared secret key securely. But whenever it is implemented, it was working well. But later on, the people come with the idea that Diffie-Hellman key exchange algorithm has a certain loophole, and due to which it is not safe to use the Diffie-Hellman key exchange algorithm for exchanging the shared secret key. So we have certain problem with the Diffie-Hellman key exchange algorithm. So we have now what is the problem which is related with the key exchange algorithm, and that problem is known as meet in the middle attack or bucket brigade attack. Now, what is the meaning of meet in the middle attack or the bucket brigade attack? A meet in the middle attack is known just because that two persons are in conversation, two persons want to exchange the shared secret key. A person who is sitting in between is going to give uh, some attack on these two people in such a way that it is going to breach the security by which the Diffie-Hellman key exchange algorithm can take place, and they are able to agree upon the K1 and K2 is equal to K. This is also called bucket brigade attack because in the previous years when we were not so developed, in case that this bucket brigade is being used by the fire people, fire extinguisher people, who used to carry the bucket full of water as well as sand to finish wherever the fire is, and they are in a line, and one bucket is being carried by a person, handed over to another person, that and similarly the person who is putting in a certain line carries the bucket from the source point to the destination point where the fire is on, just to remove the fire. So that is why it is called meet in the middle attack as well as the bucket brigade attack. Now, what actually that attack is and how we can uh, understand that how it is possible. Now, the first point is if Alice wants to communicate with me securely, and it will be using Diffie-Hellman key exchange with him. And for this purpose, Alice has sent n is equal to 11 two large prime numbers and g is equal to 7 to the Bob, which will be used to calculate later on the value of K1 and K2. Alice does not realize that attacker Tom, who is sitting in between, is listening quietly and picks up the value of n and g and also forwards these values it to the Bob as the original one. So, meaning thereby the first first part of the meet in the middle attack is whenever Alice is sending n is equal to 11, g is equal to 7 to the Bob, it is going to the Bob through the Tom, which is also having n is equal to 11, g is equal to 7, because it has interrupted Alice to receive n is equal to 11, g is equal to 7, and then send it to the Bob. So everyone is now having n is equal to 11 and g is equal to 7. Now let us assume that Alice, Tom and Bob secretly assumes the random number x and y as. So Alice has assumed x is equal to 3, Bob has assumed y is equal to 9, and Tom, who is sitting in between, has assumed x is equal to 8 and y is equal to 6. Now, why Tom has used these two values, x is equal to 8 and y is equal to 6? Because he does not know. Tom is not knowing that Alice has assumed x is equal to 3, and Tom is also not knowing that Bob has assumed y is equal to 9, because these are the secret values which has not been shared in between Alice and the Bob. So Tom is not able. So Tom, whatever he has done, he has assumed himself a fresh, a new value of x and y besides whatever is the x assumed by the Alice or the y which is assumed by the Bob. Now all these three persons now calculate the value of a and b. Alice calculates a, Bob calculates b, and Tom calculates a and b both because it has assumed x and y both. Now the real drama starts from this place. So Alice, how it will be calculating a is equal to g to the power x mod n, that is equal to 2. Bob will be calculating g to the power y mod n, it is equal to 8. And Tom is calculating both the values a and b. Now a is coming around 9 and b is coming around 4. Now Tom, whatever it is calculating the value of a and whatever it is calculating the value of b, a is being calculated by g to the power x. So here x is equal to 8. Here b is equal to g to the power. So here value of y is equal to 6, which is being assumed by the Tom. Here x is equal to 3, which is assumed by the Alice. Here y is equal to 9, which is assumed by the Bob. And so in this way, Alice has calculated a, Bob has calculated b, and Tom has calculated both a as well as b. Tom has calculated both a as well as b. Now the real drama begins. What is the Diffie-Hellman Key Exchange algorithm says? To send the whatever it has calculated as a is equal to 2 to the whatever it has calculated a is equal to 2, it has to be sent to the Bob, and Bob, whatever it has calculated as b, it has to be sent to the Alice. But what Tom is doing, Tom is intercepting the messages which is in conversation. Alice is in conversation with Bob, or Bob is in conversation with Alice. Whenever it sends a is equal to 2, it keeps that a is equal to 2, intercepts it, and keep this a is equal to 2 with himself, and whatever it has calculated as a is equal to 9, it will send a is equal to 9 to Bob. Whatever Bob has calculated b is equal to 8, it will be sent, Bob will send this to Alice, but instead of going to Alice, intercepted by the Tom, and put this b is equal to 8 with itself, and sends whatever it has calculated b is equal to 4 to the Alice. So meaning thereby, Alice wants to send a is equal to 2 to the Bob, but Bob has received a is equal to 9 by the Tom. What Bob has sent, b is equal to 8, it is meant for Alice, but it has been intercepted by the Tom. It keeps that b is equal to 8 with himself, and send b is equal to 4, whatever it has calculated, to the Alice. Now Alice and Bob is knowing that they are in conversation with each other, but it is not so. Tom is sitting in between, is calculating its own values and keeping those values which is coming from Alice and the Bob to itself, and whatever it has calculated the value of a, it sends it to the Bob, and whatever it has calculated as b, it sends it to the Alice. So therefore at this particular juncture, Tom and Bob have the value a and b as shown like this. Alice is equal to a is equal to 2 and b is equal to 4. Tom is having a is equal to 2 and b is equal to 8. And Bob is having a is equal to 9 and b is equal to 8. Now you see the star which is the red. A star means this is not actual b. Actual b was 8. But since the 8 has been intercepted by Tom, and whatever it has calculated sent to the Bob, so Alice has received b is equal to 4. Now a is equal to 2, it has to be received by Bob, but here in this particular case it is receiving a is equal to 9. Now, based on these values, now all three persons now calculate their keys and how they will be calculating. Alice will be calculating K1, Bob will be calculating K2, and Tom will be calculating K1 and K2 both. So how K1 will be calculated? B to the power x, it will be coming as 9. Bob is calculating K2, it is coming as 5. So you see, whatever Alice has calculated and whatever Bob has calculated, Alice has calculated K1 as 9 and Bob has calculated K2 is equal to 5, which is not same. Why it is? Because why it is so? Because the Tom has changed the value of A and B, and Tom has calculated K1 is equal to 5 and K2 is equal to 9. Now what will happen now? Now Alice, which is having 9 as the key, will encrypt its message using the key 9, and it will send that encrypted message for the Bob. It is being interrupted by Tom, and by using K2 that is equal to 9, it will be able to decrypt it, and after decryption it will be read all the secret messages. But Tom also is a very clever person. He doesn't want that Alice and Bob should know that there is a person in between. So what he will do, after decrypting the message will become in the plain text form. So what it will do, it will encrypt that message with the help of this K1, an encrypted message it will send it to Bob. So what Bob will be doing, it will be using 5 to decrypt the message. So similarly, whenever Bob has to send any message, it will encrypt the message with the 5, which will not be received by the Alice. It is being intercepted by Tom. With the help of K1 is equal to 5, it will decrypt it, understands it, reads it, and then it will again encrypt with the value K is equal to 9 and send it to Alice. So whatever Alice is sending, it is received by the Bob. Whatever Bob is sending, it is received by the Alice. But there is a person who is sitting in between as a Tom, is able to decrypt all the messages, read all the messages, interrupts all the messages, and all the kinds of security is being breached. So this is the problem with this problem is known as meet in the middle attack, or it is also called the bucket brigade attack. Why it is called meet in the middle attack? Because the person is sitting in the middle in between these two persons. That is why it is called middleman attack or meet in the middle attack. And why it is called bucket brigade attack? Just because of the analogy that whatever information is sent by Alice, it has to be received by Tom, decrypts it, again encrypts it, and then it sends it to the Bob. Bob, whenever it is encrypting any message, it is being received by the Tom after decrypting, and again it is after encrypting it is. So there is a person who is serving as a bucket brigade. That is why this attack is also known as bucket brigade attack. So that is all. Now, of course, there is a solution of this kind of problem. Because in this particular case, whenever Alice and Bob are in conversation with each other, they are not, before any conversation, they are not supporting anything with which they are able to be sure that whatever conversation is going on, they are talking to Bob or they are talking to Tom. So that is why the new concept of another principle of cryptography has to be introduced, and if that new concept of cryptography will be introduced, the Diffie-Hellman Key Exchange algorithm will be safer. And what is that principle of security? That principle of security is called authentication. Before you start conversation with anybody else, first you authenticate whether the person to whom you are talking about is that same person or is the different person. So if authentication is being implemented in this particular case, before the Diffie-Hellman Key Exchange algorithm could take place for exchange of the key or the shared secret key, then this problem of the Diffie-Hellman Key Exchange can be avoided.